All right, you guys, so here is the 2010 for response number 6. It's a non-calculator problem. And there's not like a big part of the stem of the problem. It just says in the directions, solutions to the differential equation dy over dx equals xy cubed. So here's our operator notation for this first derivative in terms of both x and y. Also satisfy, and this is kind of a different twist, the second derivative of y with respect to x twice, right? That notation is operator notation for the second derivative of y with respect to x, equals y cubed times the quantity 1 plus 3x squared y squared. Let y equals f of x be a particular solution to the differential equation dy over dx equals xy cubed. So y equals f of x is like our original function that will give us this first derivative, with f of 1 equaling 2. So isn't that my initial condition? So I have 1 comma 2, this is my x, this is my f of x, or my y that corresponds with that. And this is a 3-part problem. So there's a part A, there's a part B, and a part C. So part A says, write an equation for the line tangent to the graph of y equals f of x at x equals 1. So when you have to write an equation for a line, I've seen a few times on these separable differential equation problems. This one just doesn't have a slope field at the beginning. That you guys will try and do the separate differential, separate the variables and solve the differential equation when you're just trying to write the equation of a line. If you do that part in the wrong part of the problem, they will not go, oh, this part really is supposed to be down here, and bring it down for you. So you would lose all the points for that. So if we want to write an equation for a line tangent to our rule at x equals 1, you've got to go back to the basics. What do I need to write an equation of a line? Oh, I need a point. This is my point. The point that they're telling me is our initial condition. Oh, I need a slope. This represents the slope, right? The slope is the derivative in general, and I just need to find the slope at the point in question. So, yeah, I have a differential equation that's in terms of x and y, but I know the whole point. I know the x and the y I'm supposed to be plugging in to evaluate the slope at this point. So use that evaluation bar, and we're supposed to be evaluating the slope at 1, 2. So we're going to replace our x with 1, we're going to replace our y with 2, and we do exponents before we multiply, so 2 cubed is 8, and 8 times 1 would stay 8, and there's my slope. So my equation would be y minus 2 equals my slope 8 times x minus 1, and there's my point slope form, and I don't need to do anything else. That is one version of an equation of a line, and that's honestly where you should stop so you don't accidentally distribute or try and isolate y and miss anything doing something dumb in your arithmetic. Part B says to use the tangent line from part A. Oh, okay, so now we got to go back and actually use a answer. That doesn't happen very often in calculus, that you go back and use the answer in a prior part of a problem to solve something else later on. Usually you can enter any part at any moment in time, but in this case we do. Use a tangent line equation from part A to approximate f of 1.1. So we want to find the approximate answer for our real function f at the input value of 1.1. And then they say, given that f of x is greater than 0, for 1 is less than x, which is less than 1.1, they're giving us an inequality thing. If we did that interval notation, it would be from 1 to 1.1 with open parentheses. Is the approximation for f of 1.1 greater than or less than f.1.1? And explain your reasoning. So we're going to get to that part in a minute because that part's kind of a mess. Let's just do the linear approximation. Remember, that's what this is called, because we are using a tangent line to approximate an actual function value. The tangent line isn't going to give us the actual value, but it's because it's close, right? 1, this is the tangent line at x equals 1, is pretty close to 1.1, so it's a decent approximation. Well, before I can really do this and find this approximation, maybe I do want to isolate this for y, so that I can think about just plugging it in. Well, I would add the 2 over, so that would isolate y, but I'm not going to distribute. I'm just going to leave it like this and add the 2 on the end. That's another acceptable point slope form version. And if they're telling me y equals f of x, then really like I can think, oh, so if I change y to f of x, here's what I have, and now I'm using 1.1 in place of every x I see, and this is going to be a pretty close approximation because this tangent line is pretty close to what's happening in the function at this moment in time. So it's approximately 8 times 1.1 minus 1, and behind it plus 2. And that's where I would stop. I would not go farther. So guys, what I'm saying is a lot of you, when you're turning in homework on problems that look like this, you'll have it written here, and it's supposed to be non-calculator, and then you'll just jump to a final answer. And I'm like, really? You did all that arithmetic without a calculator in your head and just went straight to a final answer? Doesn't seem like it. Seems like either you use your calculator or you're writing it straight off the rubric. And both of those things are cheating yourself, so I don't know why you're choosing that. I mean, we're putting in a lot of time and effort to make videos. If you guys are just looking crap up on the internet and not really using the videos and trying to learn from it, you're only hurting yourselves and you're ruining the trust that Hernie and I have with you. So I don't think that that's a very wise decision. All right, so now going back to the whole part, now that we have that approximation of whether it's an over or underestimate. So it says, rereading, right? Sometimes you have to reread, especially when it gets wordy. Given that f of x is greater than 0 on the interval 1 is less than x, which is less than 1.1, is the approximation for f of 1.1 greater than or less than 1.1? So we know that a linear approximation, whether it's an over or underestimate, is based on concavity. Maybe that's why we have the second derivative, because isn't the second derivative sign going to give us information on the original function's concavity? But them telling us that information about f of x being greater than 0 on that interval from 1 up to 1.1, that has to be important, or they wouldn't have told us that. So you guys think about this. They're saying the original function is greater than 0 on that interval. Isn't f of x just the same as y? So even if I thought about, oh, this is the same thing as y is greater than 0. Doesn't that mean y is always positive? Or your outputs are always positive? Or your graph on this interval is always above the x-axis? So this means that y, or f of x, is always positive on at least this interval. The interval from 1 is less than x, which is less than 1.1. Or if you want to put it in open interval notation, parenthesis 1, comma 1.1, and your parenthesis. Okay, so now if we have the whole idea that we understand, this would be one of those things you want on your list of things to know paper, that the tangent line approximation being over under estimate is based on the second derivative. That's probably why they gave us the second derivative. Then the second derivative of y with respect to x twice. Well, if now I know y is always positive, this would be a positive number cubed. This would be a positive number squared. And x on this interval, right, in between 1 and 1.1, that's definitely a positive number. So if I thought about this, just plugging in numbers, I'd have a positive number cubed. In parentheses, I would have 1 plus 3 times a positive number squared times a positive number squared. And wouldn't all of this stay positive? So that's just me thinking it out. But I'm doing a positive number cubed. That stays positive. All this would be a positive. I'm multiplying two positives together. So that means that my second derivative of y with respect to x twice is greater than 0 on our interval from 1 is less than x, which is less than 1.1. But I couldn't immediately get to that without knowing this and thinking it through a little bit. And by the way, I haven't really stated my conclusion. I just had to think it through. So if our second derivative is always greater than 0 on this interval, then we know our original function f is concave up, right? Second derivative is positive. That means our original function is concave up on the interval from 1 is less than x, which is less than 1.1. So draw a little picture. If I draw something that's concave up, holding the water in, and I thought about a tangent line right there. Well, the tangent line, to only touch that curve in one spot, would have to be underneath our concave up curve. Even if I drew it concave up decreasing, my tangent line would still be underneath. If the line is under the curve, then the approximation is an under approximation. So my final thought, putting all of this together, this is at least how I said it, is therefore the tangent line approximation of f of 1.1 will be less than, because that's how they worded it in the problem, but if you said an under approximation or an underestimate, that's fine, will be less than the actual value of f of 1.1. And my picture kind of puts it in my brain, but I have the second derivative work and reasoning to prove it. And so this is my final answer for part B. Okay? So part C is now the real algebra heavy part of the problem. So it says, find the particular solution y equals f of x with the initial condition that f of 1 is equal to 2. So our same initial condition that we have the whole time, 1, 2. Okay, so now I really want to solve the differential equation. The only technique they can test you on is the separation of variables technique. So if it doesn't seem like you can separate the variables, they must not be asking that question. And you can't have the work for part C in part B. You can't have that. You have to know what you're doing for each part of the problem. So if I want to separate that, this is something that I can definitely separate because it's a product. It usually has to be like a product or a quotient, or you have to be able to factor to turn it into a product and a quotient to get the y's and the dy's to one side and the x's and the dx's on the other. Or if it's a context problem, whatever variable, and it's like derivative variable on one side and the other variable. If we have things both in terms of y and x like we do in this problem, then we definitely want to separate. Sometimes you might have a differential equation that might be only in terms of one letter. If you have a constant, put it on the x side. Okay, so I would think divide by y cubed or multiply by the reciprocal, 1 over y cubed, dy equals, the x stays on the right hand side, and multiply by dx to move that over. And then don't we want to take our integral of both sides? So kind of doing this in general right now, right? Since we don't have boundaries. Because this is not natural log of absolute value of anything. This is going to be bring it up, make it to the negative third, so I can power rule it. So I'm going to add 1 to the power, so negative 3 plus 1 would be negative 2. Divide by that power, so I'm dividing by negative 2, equals add 1 to the power, which gives me 2. Divide by that power, multiply by the reciprocal, 1/2. You could also multiply by negative 1/2 right there. And then because I'm all done integrating both sides, I got to have my plus c right there, so I have my constant of integration. So I maybe do want to write this as a negative 1/2. I think that's cleaner than divide by the negative 2. And then right now, I'm going to use my initial condition. So my initial condition was that y was 2 when x was 1. So negative 1/2 times 2 to the negative second equals 1/2 times 1 squared plus c. So 2 to the negative second, I would want to drop down to the denominator and make it 2 to the positive second. And it's down with this 2. Equals 1 squared would stay 1, so this would just be 1/2 plus c. 2 squared would be 4 times the other 2. You do need to know your powers of 2 pretty well. Will give us 8, right? So this would be negative 1/8 equals 1/2 plus c. Non-calculator, subtract the 1/2 over. So halves in terms of eighths would be what? 4. So this would be negative 1/8 minus 4/8, which would give me negative 5/8. And we've been talking to you about this the whole time we've been doing separable differential equations. The biggest bulk of your points is going to be right there. If you can't finish the algebra to solve for C, don't have a panic attack. It's the last point. It's the hardest point to earn. It's very time consuming usually with the algebra. Like you just have to let it go if you need to let it go. Mr. Herney, do you want to sing it, Let It Go to them?
Let it go!
Okay, so back to this point. Negative 1/2 y to the negative second equals 1/2 x squared minus 5/8. So now if I need to find my particular solution and solve for y, this is where the algebra just gets like messy, right? I am going to try, I have the time to earn my last point. So maybe I want to bust some fractions out right here. I don't know. So if I multiplied through with a negative 8, maybe, so I don't have a negative in front of the y, wouldn't that bust the fractions out? And I want to do that to every term on both sides to get rid of all those fractions. Maybe that will seem easier to deal with. So that negative times the negative would turn positive. 2 goes into 8 4 times. So this would turn into what? 4y to the negative second equals here. It would introduce a negative. 2 goes into 8, negative 4 times. Negative 4 times x squared gives us negative 4x squared. Here this negative times a negative turns to a positive. The 8's would cancel and we would just get plus 5. So this is really 4 over y squared equals negative 4x squared plus 5. Now you could either multiply both sides by y squared and then divide by your whole quantity and then think about taking the square root of both sides to get rid of the squared sign. I'm going to show you a different option because kind of Herney showed you that option on the last problem. I would think of this. If I have a fraction on the left-hand side, how about I real quick make the right-hand side a fraction, right? Couldn't I just say, oh, it's really these two terms over 1? And if I have a fraction equal to a fraction and what I want to solve for is in my denominator, can't I just reciprocate each fraction on each side? So this would turn into y squared over 4 equals 1 over negative 4x squared plus 5. And I'm going to multiply both sides now by 4 to get my y squared all by itself on the left. So I would have y squared equals 4 over, maybe just to make this look cleaner, I'm going to put the 5 in front, 5 minus 4x squared. And the thing that undoes a squared sign is going to be the square root of both sides. And I'm going to do a great big square root over that entire fraction. And I'm running out of space super, super duper bad. I don't know where I can erase or move to. I'm going to move right here in this little area. I don't know. So I would get y equals plus or minus big square root of 4 over 5 minus 4x squared. But it can't be both versions. You got to pick the appropriate branch. And a lot of you can tell kind of immediately, oh, the appropriate branch, if here the y is positive, is going to be the positive branch. But if you need to like show it, if I plug in x as 1, 1 squared would be 1, 5 minus 4 would be, because the 1 times 4 would just stay 4, would be 1, 4 divided by 1 would be 4, and the square root of 4 is 2, and we don't want the negative there, because otherwise that would turn it into negative 2. So you can't leave it as plus or minus. You have to choose the appropriate branch. So y would equal the positive branch, big square root of 4 over 5 minus 4x squared. There's different versions that you could get depending on if you got rid of the fraction back here by multiplying by 8 or if you did something different. So there are definitely multiple acceptable versions that are all equivalent. Some of you might remember, oh, if it's the square root of a fraction, I can square root the top and square root the bottom. The square root of the top would turn into 2 because the square root of 4 is 2. But I can't do anything with the radicand on the bottom since there's 2 terms. So this is also the same answer. So kind of like either one of these are okay as final answers. But you gotta think about which version that is, that plus or minus thing. Okay? I even had a different version on my paper when I didn't get rid of the 8 right away, and I had the square root of 8 over 10 minus 8x squared. That's the same because they're all just really divisible if I factored out a 2, and then it would reduce to the same expression. So doesn't really matter. If you have an equivalent version that matches that, then you got those points for that problem. So speaking of points, let's go through them. So part A is 2, so you get a point for finding your slope to be 8, and then you get 1 point for your equation, of course, of your tangent line, and I would have just left it in slope-intercept form. Even though like later on in part B, I kind of have to clean it up and get it in function form so I can estimate or approximate f of 1.1, I would leave the tangent line in slope-intercept form for part A, or in point-slope form for part A. So part B is also 2, so you get 1 point for your approximation. I would have stopped right here. The approximation using the equation of the tangent line to approximate f of 1.1. If you worked it all the way out, you're dumb, but if you did, you do get approximately 2.8. And if you had different versions of that, like that are all equivalent, that's fine too. Like we'll read your work with you on that part. And then the second point is that the tangent line is going to be less than, however you said that, an under approximation, smaller than, less than, an underestimate of the actual value. But you kind of had to have this answer with a reason. So if you didn't link it somehow to the second derivative being positive on that interval, because it's not everywhere that the second derivative is positive, but it's second derivative being positive on that interval, then you're not going to get that. So that's conclusion with that reason is going to be a pretty hard point to earn. Because if you kind of said something incorrect, then you're not going to get your reasoning point. Okay? And then the last part, part C, is 5. So we're pretty used to this by now. So you get a point if you separate your variables. You get, on this problem, only 1 point for your antiderivatives. So both sides had to be correct. So if you didn't get both sides correct with your antiderivatives, you're kind of like already out of luck on this whole part C. This was back in 2010, so in this year you got 1 point for your plus C and 1 point for correctly using your initial condition. And remember, you guys, when we're saying you got to use your initial condition, if you plugged them in backwards, you wouldn't get that point. You do have to use it correctly. And then you have to do all that algebra, which like took me like all of this spot to solve for C, all of this spot to get rid of my like bad fractions, flip it around, deal with negative exponents, take the square root, choose the correct branch, all of that blah, 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 blah stuff. But then finally, your last point is, did you have one of these versions where you solve for Y? And that can be difficult with the algebra. They usually make that point pretty difficult to get correct. Okay? So make sure that you're getting the hang of these, because being able to do separable differential equations is usually something that is tested on free response on the AP exam. All right, talk to you later.